Chapter 7 deals with chemical formula relationships. So let's talk about chemical formula. In fact, let's talk about composition. There are different ways to express composition. Probably one of the most common ways of expressing composition is by percent by mass. Like swimming pool water. What's the percent by mass of certain species? Sometimes the percentage is too big, sometimes an extremely small percentage by mass. So we use parts per million or parts per billion or something like that. But all those are for composition. So we could do an example here. Let's take water. How would we figure out what the percent by mass is? Well, what is water anyway? Water is H2O. H2O, that's not the composition by mass. H2O is a composition by atoms. 2 hydrogen atoms for every oxygen atom. If we want to figure out the percent by mass, well, hydrogen atoms and oxygen atoms weigh different amounts. For example, a hydrogen atom weighs about 1 U, an oxygen atom weighs about 16 U. An oxygen atom is 16 times heavier than a hydrogen atom, so considerably heavier. And so if we do percent by mass, we've got to figure out, we have 2 H atoms, and how much does an H atom weigh? Well, H atoms weigh different amounts depending on which isotope we're talking about. Right? And since we aren't going to be so focused on individual isotopes, we just want the average hydrogen atom. And so the average hydrogen atom weighs 1.01 U. Let's do 2 decimal places here. Or 1.008 U. That would be to 3 decimal places. In other words, this is to 3 sig figs. This is to 4 sig figs. But in terms of these masses, I look at it in terms of decimal places because we have to combine the masses of all the atoms together. And so this is the one we're going to use for H in compounds. And then this one we'll use for atomic hydrogen. An atom of hydrogen on average weighs 1.008 U. That gives us 4 sig figs. Or elemental hydrogen, that is, or H2. Normally when we think of hydrogen, we think of H2. And so if we have 2 hydrogen atoms, it gives us 1.016 U, or not, 1.016, not 1, sorry, 2.016 U. That gives us 4 sig figs, versus this, which would give us 3 sig figs. Well, this is hydrogen in a compound. We have 2 hydrogen atoms in H2O. We also have an oxygen atom. The average oxygen atom weighs 16.00 U. And so if we do this, since we're using hydrogen in a compound, we care about the decimal places. I want 2 decimal places in the weight of my water. And so an H2O molecule, on average, is going to weigh 18.0. Actually, what am I doing? This is 2 times 1.01 U, which gives us 2.02 U. So it comes out to 18.02 U. This should be separate here. Like that. And so hydrogen atom weighs 101. We got 2 of them. That gives us 202 plus an oxygen atom, which weighs 16 U, which gives us an average weight of the water molecule. The average weight of the water molecule weighs 18.02 U. The strange thing is there's no water molecule that weighs 18.02 U. You're going to have water molecules that are going to be slightly less, and then you're going to have water molecules that are more. It's just the average. It's like, what's the average of a $5 bill and a $10 bill? $5 and $10, the average of that is $7.50, right? Is there such thing as a $7.50 bill? No, you either have a $5 or $10. It's the same thing here. We aren't going to find a water molecule that weighs weighs this, but that's the average. Well, that's the mass of the water, and so if we want the percent by mass A, so percent A by mass, then all we need to know is the mass of A over the total mass times 100%. And so here we can get the percent hydrogen. The percent hydrogen, H by mass. Now this, when I say percent hydrogen, I'm not talking about H2 because this is a percent hydrogen in water. Even though it is an H2 here, it's not H2 gas. You know, it's just H. And we just happen to have 2 of them. We could have had 3 of them, we could have had 4 of them. So this is percent H by mass, not H2. And so the percent hydrogen atoms by mass is just equal to the mass of the hydrogen. The mass of the hydrogen is going to be 2. Okay, now we have a tricky situation here. The reason I put this at 2 decimal places is because I know I'm doing an addition. If you do an addition, then you're going to round this to 2 decimal places. But here, I'm changing this a little bit because we're doing multiplication. If we're doing a multiplication here, I'm going to use the second one, 1.008U. Yeah. So this is going to give me 2.016U divided by the total mass of 18.02U times 100%. This will give me 4 figs in the percent by mass. And so this is going to be 2.016. Calculator. Have to use this. We have 2.016 divided by 18.02 times 100, 11.187. So we get 11.187% hydrogen by mass. All right, there's only 2 things here. So the percent oxygen we can get in two different ways. The first way is we could just take 100% minus 11.187. So if it's 11.187% hydrogen, then the rest has got to be oxygen. So 100 minus 11.187. Okay, the other way is we can just calculate it. If we calculate it, you know, it's just the percent oxygen is going to equal the mass of oxygen, 16.00 over the total mass, 18.02 times 100%. So let's see what this gives us. So if I take 16 divided by 18.02 times 100, 88.79. So this gives us 88.790%. Look at it, they're different. You know, if I look at this, if I just take the balance being oxygen, I get 88.81. If I just calculate it straight off here, I get that. And so first thing you look for is an error, and there's pretty much no errors in the calculation. So why are they different? We should be getting the same exact percent oxygen using both methods, but we're getting a slightly different answer. Why is that? In fact, if I add these 2 numbers, they should add up to 100% because this is just made up of hydrogen and oxygen. And so these 2 combined add up to 100%, but these 2 combined do not add up to 100%. This is just slightly less than 100%. Let's see what it is. It's going to be 11.187 plus 88.79. 88.79. That gives me 99.977%. So I'm missing something because I only get 99.977%. I'm missing 0.033% of the mass. Where did it go? Where did that 0.033% go? 0.00, is that part of the mass defect?
Yes.
Is it? mass defect? No. Do you know what it is from? Round-off error. And so that's okay. We're within what you expect from round-off error. Sometimes when the numbers don't add up, you wanna first look for a round-off error and then look for mistakes. I mean, if it were more than 0.033, I'd start worrying. For example, if it were 0.3%, then either you're having huge round-off error or there's an error in your calculation. But something like 0.033% is probably due to round-off error. Which one do you think is more accurate, A or B? A. Yeah. We're okay there. So that's one way of representing. We can represent by percent by mass. And so if you think about water, water is mostly oxygen by mass. But when we look at the atoms, the water is not mostly oxygen. So if we look at percent by atoms, then it's the same type of deal. If we want the percent of A, it's going to be the atoms of A over the total atoms times 100%. And so, what would the atoms of, okay, so we're looking at percent hydrogen. Percent hydrogen would be how many atoms of hydrogen? 2 atoms of hydrogen. Over how many total? 3 atoms total. Times 100%. This is going to give us 66.6, that's 2/3, so 66.66. Let's just keep going, percent hydrogen. And so by mass, it's only 11.19% hydrogen. By atom, it's 66.67. So we definitely have more hydrogen atoms. And the percent oxygen would just be the balance, which would be 33.33%, or 1/3. In other words, 2/3 hydrogen, 1/3 oxygen, percent by atoms. Okay, percent. Rather than doing percent by atom, we do atom ratios. The atom ratios are the formula. See, atom ratio. You know, 2 parts of hydrogen, 2 atoms of hydrogen for every oxygen. So we call this the chemical formula. And then finally, we could have the mass ratio. The mass ratio is not as useful. That would be hydrogen, 11.19 parts of mass, oxygen, 88.81 parts of mass. In other words, that would be the mass ratio. The mass ratio is not going to be nearly as useful, but it's something we think about as well. Okay, why don't you do this here? Okay, let's calculate the mass of ammonium nitrate here. Okay, try that. Calculate the mass of ammonium nitrate. Okay, so what did you get so far? Well, if we want to know the mass for ammonium nitrate, first thing we got to know what it's made up of. So normally what it's made up of is the chemical formula or the atom ratio. So we need the formula for ammonium nitrate. What's the formula for ammonium? 1H4 plus. And nitrate? NO3 minus. And so ammonium nitrate is just 1-to-1. Do it. NH4 NO3. We know the average mass of each of the atoms, so we just have to figure out how many atoms of each we have. So how many nitrogen atoms? We have 2 nitrogens. And then the way we do it, for compounds, we're going to go 2 decimal places. And so I want the mass of nitrogen to 2 decimal places. What would it be? What'll it be? 14.01. So I'm going to go 2 times 14.01. Now, in the past, what I've said is don't round. Don't do intermediate round-off steps. If you do intermediate round-off steps, we're going to just be compounding the round-off error throughout the calculation. But here's a case where to maximize accuracy, you don't want to do these intermediate round-off steps. But to maximize speed, what we're going to do is we're going to round off all the elements to 2 decimal places, which could lead to differences in the masses compared to what you might see in a book or something like that. And so for nitrogen, we'll just call it 1401. And then 2 of those will give us 2802. Okay, the units here would be in U. That's how much it weighs. Okay, then how many hydrogens do we have? 4. Now these hydrogens, are we going to use 101 or 1008? We're going to use 101 because these hydrogens are in a compound. This is going to give us 404. And then how many oxygens? 3 oxygens. And if you look at oxygen to 2 decimal places, what would oxygen be? 16.00. So this is going to be 3 times 16.00, which would be 48. 48.00. Okay, so that gives us 6, 0, 16 plus 20, 80.06 U. And so what should I say, 1 molecule of ammonium nitrate? 1 molecule of ammonium nitrate weighs 80.06 U? No, because does ammonium nitrate form molecules or does it form a lattice? Well, first thing we ask is ammonium nitrate a molecular compound or is it an ionic compound?